Okay, so yeah, welcome back. And in the morning, I discussed the large gauge transformation and application to the system with fractionalization. But I had to quickly wrap up the discussion, so I want to supplement some discussion about more subtlety or more precise formulation of the consequences of fractionalization. So to recap, I was discussing a fractionalized system. So which means that my system consists of some microscopic particle like an electron with elementary charge. E. Then out of the system, there are elementary excitations in the form of quasi-particles and quasi-hole with fractional charge with respect to this elementary charge E. So this is a assumption. And also, I suppose that the system is gapped. Then I introduced two operations. That is, one process is creating a quasi-particle hole pair and drag them around the system. Then pair annihilate. Let's say this is X. And also inserting this AB flux from 0 to phi 0. So adiabatic flux insertion. Then my point was that this Fx and Lx do not commute because if you apply Lx after flux insertion, then you move around the quasi-particle with the background vector potential, background gauge field. And even though this unit flux quantum is a magnetic flux such that there is no AB effect for original particle, electrons, but for this fractionally charged particle, you can still feel this magnetic flux. So the AB phase you would acquire would be 2 pi I P over Q. So this fraction of the charge carried by quasi-particle or hole. And okay, and I forgot to say that P and Q are integers and mutually prime coprimes. That is, P and Q don't have common factor. If they have common factor, you divide by common factor to make them coprimes. Then you would have this kind of commutation relation. But actually, this is not yet enough to derive the ground state degeneracy because this operator fx introduces the magnetic flux phi 0, and then this Lx would be some time evolution process with certain Hamiltonian with maybe potential perturbation or something, and you move the potential slowly. But anyway, this process is done in the presence of non-zero vector potential. Whereas when you apply this Lx first, this Lx is done with zero vector potential. So actually, these two operators are somewhat different because of the vector potential. So more precisely, this Lx is some operation done with the background magnetic flux or background gauge field. And this is the same operation, but done with in the absence of background vector potential. So they are, precisely speaking, different operators. So even if you have this kind of relation, you cannot immediately conclude that the ground state must be degenerate because these two are actually different operators. So if they are different operators, you multiply these different operators, then you get a different phase factor that, that's, you cannot conclude anything directly from here. But then we can recall that these two operators represent the same physical process, creating quasi-particle Hall pair and dragging this quasi-particle around, then annihilate quasi-particle Hall pair. So they are indeed almost the same operator, but the only difference is this background gauge field. So that means that, so as I said, this Lx must be given by some time evolution with respect to some time independent Hamiltonian. So I don't specify exact form of this, but you can introduce some potential perturbation or something, and you move the potential around. So then, as I said, only difference between these two background vector potential, and everything can be, at least in principle, defined for microscopic model. So everything can be written in terms of electron operator, the original constituent particle. So that means that, and also this Lx can be written as a time evolution operator. So that means that this Lx with this unit flux quantum inside must be gauge equivalent to, maybe this is opposite, but anyway, it is. So because this time-dependent Hamiltonian should be related by this large gauge transformation. So the time evolution operator Lx must be also related by this large gauge transformation. So using this, you can rewrite this equation. So more precisely speaking, Lx phi 0 fx is fx and you can replace this with this gauge transformation form. So, and then you can apply this UX inverse from the left. Oops. Sorry, I thought fx. So here Lx is just this Lx at 0 vector potential background. So this is, and now we can define a new operator that is Ux inverse times fx, and maybe we can define this as fx tilde. So this is again fx tilde. So in this way, now this shows a commutation relation between the same set of operator, fx tilde and Lx. So Lx times fx tilde does not quite agree with fx tilde times Lx. And now this Lx and Lx are the same operator at this process with a 0 background gauge field. And you have this factor. So now from this, and by the assumption that both Lx and fx brings back the ground state to ground state, you can derive the ground state degeneracy. And here, actually, this new operator fx tilde has a physical interpretation. That is, you adiabatically insert the unit flux quantum, but then after insertion, you have non-zero vector potential. But by applying the large gauge transformation, you can eliminate the vector potential. So this combination, fx tilde, actually inserts the flux adiabatically, but then after inserting unit flux quantum, you eliminate the gauge field vector potential by large gauge transformation. So you are coming back to the original gauge. So that is why now this Lx and Lx both are the same operator acting on with 0 background vector potential. And now we can talk about a commutation relation. So the now we can say that if you apply this fx tilde to the ground state at 0 vector potential, you should get the ground state. And also, if you apply this operator Lx, quasi-particle whole pair creation and dragging and pair annihilation, you should come back to the ground state. But if you have only one ground state, then you cannot satisfy this relation. So in order to accommodate this commutation relation, the ground state must be at least q-fold degenerate. Yes.
Think of this operator with gates 5. Is this an operator that acts at a fixed time, or does it continue to act at all future times?
You mean this F?
Yes.
Yeah, you can again formulate this as a time evolution. Actually,
So it's not an operator that acts at a fixed time.
Right, yeah. So this is supposed to be adiabatic flux insertion, which means that you start from Hamiltonian with zero flux or zero vector potential, and gradually increase vector potential, and you just replace this time-dependent Hamiltonian with vector potential, and vector potential you increase slowly.
Then you can feel the future.
Yeah.
It's not an operator that acts at a fixed time, but it's something that acts at all future time.
Yeah, I would define that way. But once you define fx as a time revolution corresponding to adiabatic flux insertion, this defines certain unitary operator. So after defining unitary operator, I think if you like, you can forget about the time evolution. Just apply this unitary.
But they haven't done in the future time. So here we sometimes.
Yeah.
In the future time, there's a new Hamiltonian, not the old.
Well, yeah, new Hamiltonian just have non-zero vector potential. Yeah, but my point is that you can eliminate this vector potential by large gauge transformation. Then after applying this F tilde, you come back to the original gauge with zero vector potential.
But I thought, you should think of fx as acting. So fx acts for a finite but possibly large time. Like the first grade said, you can think of as just acting at a fixed time. If you zoom out and out in time, right? That's how I always thought about it.
I thought this is U inverse F, not F itself. The way I interpreted that is that sometimes the Hamiltonian starts changing, and then you act with U inverse.
Yeah.
That's the way I interpret it. Then A acts either before or later.
Right, yeah.
This whole thing, U inverse A, acts at the finite time. F itself acts all the way to the above future. This was a question, it's not a statement.
Well, yeah, so that's my way of formulating this. But once you define this fx, then it's just like some sort of unitary operator. So you can forget about how long time it took, at least for this discussion. But what you described is how I formulated this. Okay. So this can be said for torus. But So here, I'm not using any translation symmetry or anything. So this argument can be applied for double torus and so on, higher genus Riemann surface, if you like. So if you consider the system on this genus G Riemann surface, which means that there are G holes, then you can apply the same argument for this loop and also conjugate flux or vector potential. And you can take this loop and define similar operator L beta and conjugate flux insertion. So if you have 3 holes, you can introduce 3 this quasi-particle dragging operation and 3 flux insertions, which each of these flux insertion and this L operation have the same contention relation. So in this case, you have at least q to the power of g ground state degeneracy. So that means that, okay, so if you just know the ground state degeneracy on the torus, then this could be just a result of the spontaneous symmetry breaking. But in this case, as a consequence fractionalization, we can apply the same argument for this higher genus surface and then conclude that this system must have at least q to the power of g ground state degeneracy, which means that this ground state degeneracy is so-called topological degeneracy. And this topological degeneracy is regarded as a signature of so-called topological order. So that means that once you assume the fractionalization in this sense, then you must have a topological degeneracy, which indicates that the system has topological order. So the conclusion is that if there is a fractionalization, then there must be a topological order. And yeah, I didn't include this in the reading list, but so this argument is based on my paper with Sentiu in 2006. And I also have to say that actually, even if you don't assume the fractionalization, if you assume that this quasi-particle or quasi-holes obey the fractional statistics, anyonic statistics, that is, if you exchange 2 particles, you get some non-trivial phase factor, not 1 or not -1, then this operator Lx and maybe Ly satisfy non-trivial commutation relation. So by similar argument, well, okay, that was the original argument. So if you just assume the fractional statistics, then in a similar way, you can show that the system must have topological order. And this was shown in, I forgot the year, but much earlier paper by Xiaogang. I forgot the 90 something. So the structure is very similar. So, but I wanted to mention this because perhaps this is a good example of application of large gauge invariance, because the crucial point actually is this large gauge invariance. And physically, this large gauge invariance comes from the fact that the microscopic model is defined in terms of, let's say, electron with elementary charge E. And of course, without that information, you cannot say anything, because if you don't know the elementary charge in microscopic model, then you don't know the unit of charge. So even if you find some quasi-particle with charge P over Q times E, if microscopic Hamiltonian contains a particle with same charge E star, then it's kind of trivial. So this fractionalization is non-trivial exactly because microscopic model contains only the particle with elementary charge E, no fractional charge. But in the low energy limit, somehow you can find a quasi-particle that is collective excitation with fractional charge. In that case, you can derive this non-trivial constraint. And indeed, the key in this argument was this large gauge invariance. Yes.
Sorry, there are two non-contractile cycles for each handle. Should it be Q to the 2G, or is there something else?
Yeah. So you are right that even if there is only one pole, you can take the other cycle. So in the original, this case, you can thread the flux inside this torus, and then this flux insertion does not commute if there is a fractionalization with this quasi-particle moving operation in y direction. Yes, but in general, using the other cycle for the same hole may not commute completely with this Lx and Fx. So it is possible that the degeneracy you can derive using Ly and phi y can be exactly the same with degeneracy derived by this commutation relation. So that is one reason why I said at least Q for degenerate. So this is also related to the particle statistics I just mentioned, originally discussed by Xiaogang. So because this operation Lx and Ly generally don't commute. So and this commutation relation is related to the particle statistics. So what can happen, for example, in Laflin fractional quantum state, whole state, is that as far as the action on the ground state manifold, ground state subspace is concerned, this flux insertion process actually becomes the same as the other loop operation Ly. So in that case, you cannot derive extra degeneracy. But for example, if quasi-particles are bosons or fermions, then this Lx phi x, Lx fx set and Ly fy set becomes kind of independent. In that case, the degeneracy is actually q square even for torus. So in that case, this degeneracy becomes actually q to the power of 2g. But for anyonic case, I think anyonic case, the ground state degeneracy could be bigger, but when this fx somehow becomes identical to Ly, then effectively you have only one set of non-commutative relation. Yeah.
Follow-up. Does that mean that like the degeneracy is less than because it has to have non-linear?
Yeah, if the degeneracy is less than q to 2g, then I think quasi-particle must obey some anyonic, maybe abelian, but non-fermion, non-boson anyonic statistics. Yeah, because we can show that if these quasi-particles are either boson or fermion, then this degeneracy becomes q to 2g. Yeah. Thank you. Yeah, that's an interesting point, but I skipped due to save time. But yeah, that's one interesting aspect of this. Okay. So now let me switch to a different type of applications. Now to many particle system defined on periodic lattice. So the simplest example would be square lattice. Although the discussion can be easily generalized to more general lattice or system in periodic potential. But for simplicity, let's discuss square lattice. And again, I consider the square lattice and let's say the system size is Lx times Ly. And impose the periodic boundary condition. So, and my square lattice has translation invariance. So that means that you can define a lattice translation. Let's say Tx is a translation operator which shifts every side to x direction by one lattice spacing. And okay, so for future use, let me also define a Ty, that's a translation operator in y direction. So in order to use this, let's impose also periodic boundary condition on y direction. Then the translation invariance of the system can be expressed by the commutation relation. So this Tx commutes with Hamiltonian, also Ty commutes with Hamiltonian. And as in the continuum system, the translation invariance implies the conservation of momentum. And in the continuum space, the momentum is just a generator of infinitesimal translation. But on lattice model, you only have a discrete translation symmetry. But still, you can relate the total momentum to this translation operator. That is so, for example, the x component of total crystal momentum is related to this translation operator as e to IPX. So from this, well, you can regard this as a definition of total momentum or so-called total crystal momentum. And from this expression, it's evident that this Px is only defined modulo 2 pi, because if you change Px by 2 pi, it doesn't change Tx. And this is consistent with what we know about crystal momentum. So in crystal periodic potential or inside the lattice, momentum is only meaningful modulo 2 pi. Then, okay, so actually, maybe mathematically I don't need to introduce this momentum and just consider the eigenvalue of this translation operator, but still sometimes I feel it useful to think about momentum because we have some intuition about the momentum. Yes.
So just for the upcoming argument, is it necessary that Tx and Ty commute? Maybe magnetic translation?
Good question. Yeah, so when you have magnetic flux perpendicular to this two-dimensional plane, yeah, there's can be this magnetic translation stuff that makes the, yeah, that also introduce some interesting stuff. But for the moment, let me assume that there is no magnetic flux perpendicular to plane, then Tx and Ty commutes for simplicity. But yeah, thanks. Yeah, when Tx and Ty don't commute, there are additional interesting physics. Yes. Okay. Then what I want to do is again, okay, so I have this x direction and I have this flux, or let me write this as phi x because it induces vector potential in x direction. Yeah, actually, during the break, Nati Seiberg told me that we don't need flux. We can talk about holonomy just using the gauge field, which I completely agree. But maybe just me, but sometimes this flux helps visualize some physical image about this process. So I'm using this flux to explain this stuff, but of course, we don't have to discuss about this flux, and we can formulate everything just using the gauge field or connection. Anyway, if you don't like this flux, you can forget about the flux and just focus on gauge field. But anyway, pardon me?
So we assume non-commuting translations. So isn't that inconsistent with having the magnetic flux?
Okay, so this is AB flux. So this just corresponds to uniform. Okay, so I'm choosing the vector potential in this way. And this is, so that means that you have square lattice, and AX is the enters in the hopping term in horizontal direction. And AY would enter in the vertical hopping term. But as long as you choose the vector potential in this way, this is the same everywhere, then this does not break the translation symmetry. Yeah, actually, there's a gauge ambiguity, or there is a freedom in choosing the gauge field or vector potential. And if you choose vector potential differently, then you can break the translation symmetry. But as long as you use this, you don't break. Yeah, actually, that's a point I'm going to emphasize next. So yeah, thanks for the question. So to represent this magnetic flux, I use this vector potential. And this is the same everywhere. For any horizontal link, I have this vector potential. So at least for this choice, the Hamiltonian is still translation invariant for any value of the flux. And in fact, this is very crucial for my next question. That is, I want to ask, so I'm going to do this flux insertion. So increase phi x from 0 to phi 0, unit flux quantum. And then I want to ask, what is the total momentum of the system after the flux insertion? So I start from initial state. I take some ground state. And so because Hamiltonian commutes with this translation operator, I can take this initial state, ground state, also as the eigenstate of the translation operator. So this px0 is the total crystal momentum of the ground state, which is in many cases 0, but sometimes it can be pi or something. But anyway, so we have this initial value of the total crystal momentum. And then I do the flux insertion. From phi to 0 to phi equals to phi 0. Then the question is, what is the total crystal momentum in the final? So this is my question. And in fact, this can be immediately answered. Because okay, so px is related to tx. So the time evolution of px is related to time evolution of tx. So you can use either operator, but you can, for example, discuss time evolution of maybe tx as operator. In Heisenberg picture. Then in Heisenberg picture, this time evolution is given by commutator with Hamiltonian. Okay, if you like, you can also use a Schrödinger picture. But anyway, the point is that this Hamiltonian is always translation invariant, at least for this choice of the vector potential. Then this is 0. So that means that during this flux insertion process, the value of tx or px doesn't change at all. So even in the final state, after this flux insertion, this is also eigenstate of this translation operator with the same total crystal momentum px0 as in the initial state, initial ground state. Okay, that's exact statement you can easily derive. But on the other hand, it sounds like a strange because you inserted the flux, that is, you increase the flux inside the hole. And then even classical mechanically, in classical term, this increasing flux induces electric field in x direction. So if you apply electric field to charged particles, then in general, you can expect acceleration of particles by electric field. Okay, so if the, let's say, system is insulator, maybe they are not sensitive to the electric field, but so far I'm not making any assumption. So this system may be conductor like a metal. So in case of metal, if you apply electric field, then the electrons should be accelerated. But somehow I have just shown that momentum doesn't change at all. So looks somehow strange. But of course, there is no contradiction. So the physical picture is that increase phi x corresponds to increase vector potential in x direction, which corresponds to application of electric field in x direction, and electric field should correspond to time derivative of vector potential. So then this generally expected to accelerate electrons or any charged particles. Then if electric field does accelerate the electrons, then momentum is expected to change. But I have just shown that momentum doesn't. And apparent contradictions between these two separate observations is that the momentum I have introduced here corresponds to so-called canonical momentum. So in the continuum, this is like the spatial derivative. And spatial derivative was not gauge invariant. So actually, the gauge invariant momentum corresponds to covariant derivative, which includes a vector potential. And the vector potential was increasing, although this derivative term does not. So the so-called kinetic momentum, which is gauge invariant, is increasing by increasing the magnetic flux or vector potential. So in a different way, this quantity is not gauge invariant. And after this flux insertion, as I have emphasized many times, this is equivalent to zero flux, but Hamiltonian is different because you are in a different gauge. So in order to compare the momentum between initial state and final state, you have to do the gauge transformation, large gauge transformation to eliminate the vector potential. So the Px is not gauge invariant. So to compare momentum, we should perform large gauge translation, as in the previous example. So what we need to do is, so we started from the initial state, one of the ground state, which is momentum eigenstate. And then we do flux insertion. And if we insert a flux adiabatically, the final state is nothing but this flux insertion operator I have defined previously applied to this initial state. But after applying this flux insertion operation, you are in the different gauge. So in order to compare momentum with original ground state, you need to go back to the original gauge by eliminating the vector potential by applying the large gauge transformation. And that's precisely applying UX inverse to this final state. So UX inverse fx is what I defined as fx tilde some minutes ago. So this is a final state in the same gauge as the original initial state. So let's define phi f tilde by this guy. Then now this is in the same gauge as initial state. So now we can compare the momentum. So you cannot make a meaningful comparison of momentum directly between this guy and this guy because you are now in the different gauge. So you need to apply this large gauge transformation. That is a point. Then what we need to see is eigenvalue of this gauge transformed final state with respect to this translation operator. But by definition, this is Tx Ux inverse psi f. And this is Ux Tx U Ux inverse times Ux Tx ux inverse times psi f. So now we want to know this guy. And now we recall the definition of this large gauge transformation operator, at least for lattice model we are discussing. So you sandwich this translation operator by ux and ux inverse. Then ux and ux inverse almost cancels. Okay. Of course, if there are no tx in between, then of course ux inverse is inverse of ux. So they just cancel with each other, and you get the identity operator. And likewise, here you sandwich tx with ux and ux inverse, and this translation, effect of translation survives. So you almost get the tx. And ux and ux inverse on the left and right almost cancels. But they don't exactly cancel because you shift the each side by one lattice spacing to x direction, which means that okay, so it depends on how precisely you define this tx operator, but basically you shift this x coordinate by one, by this tx. So on the left and right, they almost cancel, but this x is shifted to x plus, let's say, 1 on the right, let's say. Then they don't exactly cancel. So ux, tx, ux inverse is translation effect remains, but then this x and minus x almost cancels, but yeah, x is shifted by 1. So this plus 1 survives. So what survives is this sum of number operator. So this is a extra factor. And in general, this is an operator. But this summation over nx is nothing but the total number of particles.
That's R of an X.
Oh, sorry, NR, sorry. Yeah, thanks. Which is a conserved quantity. So, okay, so maybe I should have said this in the beginning, but the ground state also belongs to some fixed number of particle sector. So we can regard this total number of particles as constant. And also, as I said earlier, I'm generally interested in subdynamic limit. That is, so far, I'm dealing with a finite size system to make everything well defined. But after dealing with a finite size system, I want to consider the asymptotic behavior as I take the larger and larger system size. So in order to study subdynamic limit, I want to fix the density of the particle, or so-called filling factor. Number of particles. per unit cell. So filling factor, which is often denoted as nu, is the number of particles per unit cell in general. And in case of square lattice, unit cell is just a site. So for square lattice, this is just a particle per site for square lattice. But anyway, I want to fix nu and consider very different system sizes, and eventually want to consider the limit of large system size. But anyway, so for two-dimensional system, so this is like a total number of particles divided by Lx and Ly. So this total number of particles is, so n is nu times Lx, Ly. So the this means that Ux, Tx, Ux inverse is Tx times e to 2 pi I nu Ly, because Lx just cancels. And so I want to fix this nu to some fixed number, usually rational number. So again, p and q are some co-prime integers. Then, okay, this is a bit subtle business, but I want to choose this Ly to be co-prime with this Q. Then this is some non-trivial phase factor. So in this case, what happens is that Tx times psi f tilde is Ux inverse times Tx times this phase factor. But times psi f, not psi f tilde. And so this is just a number, so you can move to forward. And then Tx times psi f is, as I argued, that there is no momentum change for this guy. So this times this is just same px0 times psi f. And now you can multiply Ux inverse to psi f to get psi f tilde. So what you get in the end is e to I p x0 times e to 2 pi I nu Ly times psi f tilde, because ux inverse times psi f is psi f tilde. So now we find the eigenvalue of Tx for this gauge transform state psi f tilde, and the eigenvalue is this. So now we have extra factor, means that once you perform large gauge transformation, then generally the momentum does change, at least when this filling factor nu is not integer. So in the initial state, px was px0, and by insertion of AB flux and then doing the large gauge transformation, this momentum was changed to px0 plus 2 pi times nu Ly, which is for generic filling factor nu, non-integer filling factor nu, this is non-trivial change. So this corresponds to acceleration of particles by electric field. And, okay, so I have maybe 3-4 minutes left. And yeah. So now, again, let me assume that the system had a gap. Then, starting from the ground state, and so assume that there is a gap, and doing this adiabatic flux insertion. From 0 flux to phi 0. Then, because this is adiabatic, again, ground state, starting from ground state as the initial state, then because earlier I assumed that the gap doesn't collapse, then starting from the ground state, you must end up with the ground state. But I have just shown that after large gauge transformation to get back to the original gauge, the momentum of the initial state and the momentum of the final state must be different if nu is not integer. If nu is not integer. Yeah, of course, it also depends on the choice of Ly, but I suppose that I can choose Ly freely. So if nu is, let's say, 1/2 or something, I can choose Ly to be odd integer, and so on. Then, by appropriate choice of Ly, I just show that the final state has different momentum compared to initial state. That means that the final state must be different from the initial state. So if there is a gap, again, this implies that in the presence of gap, the ground state must not be unique. There must be multiple degenerate ground state below the gap. So the conclusion is that if the system has this lattice translation symmetry, invariance, and particle number conservation, and then under these conditions, you can define filling factor, that is particle number per unit cell. And if this filling factor is not integer, then the system is either gapless or you can have a gap, but if there is a gap, then you must have multiple degenerate ground state. So what we can rule out here is that some trivial phase with unique ground state with a gap. So the last possibility can be just excluded just from these very general assumptions. And this suggests that again, the system must be non-trivial in some sense. So, okay, so hopefully I will discuss more details tomorrow, but this ground state degeneracy signals that the system is in a non-trivial phase in some sense. Maybe it's just a conventional spontaneous symmetry breaking, or maybe this is topological order. But anyway, this suggests that the system must be, in some sense, non-trivial. And okay, so this is one generalized version of so-called Lieb-Schultz-Mattis theorem. And yeah, this follows from this symmetries of the system and large gauge invariance. And yeah, tomorrow I will mention a little bit more about background of this theorem. But yeah, this is what is known as Lieb-Schultz-Mattis theorem. Okay. So yeah, I already ran over time, so I stop here for today and we'll continue tomorrow. Thank you.
Yes, so the gap degeneracy in ground states, right? Can we argue that it has to be topological in the same flavor as the previous example?
No, in this case, this argument needs lattice translation. So this can be applied to torus, but not at least directly to higher genus Riemann surface. So what I can say from here is that the ground state must have a degeneracy on torus, but it could be just due to spontaneous symmetry breaking in conventional sense, like a charge density wave or Nail state and something like that. So it may not be topological for this. Yeah.
The problem is embedding the lattice on the higher genus surface, or like.
Yeah. So maybe you can triangulate higher genus Riemann surface, but then the system loses translation symmetry, lattice translation symmetry. So I don't know how to apply this to higher genus Riemann surface.
Yeah, so one thing I got lost is that some of these claims are basically using finite periodic lattice, right? So you have Lx and Ly, right? But then gap is a statement of so where did I lose this?
Well, okay, so I have to admit that this is not completely rigorous in any sense, but what I'm imagining is that there is a well-defined gap between the ground state and the excited states for sufficiently large but finite system size. So then we are dealing with finite system size, but above this threshold.
Okay, so when you say gapless, I should really think of it about how it scales the system size rather than.
It seems like this proof relies on the existence of a U1 symmetry.
Yeah.
Can anything be said about other symmetry?
Right. Yeah. So actually, in recent years, there are extensions to discrete symmetries and so on. And actually, there have been various different approaches, but one of the approaches I did was to use so of course for discrete symmetry, I cannot insert this flux adiabatically, but I can still twist the boundary condition according to discrete symmetry, like a Z2 cross Z2. And the argument I made was that using the twisted boundary condition, we can show that the ground state must be exactly degenerate. But then we also argue that if there is a degeneracy for twisted boundary condition, the degeneracy must also survive under periodic boundary condition. That's also not a real statement, but we have some arguments using quantum transfer matrix. So yeah, anyway, so in recent years, this has been generalized to discrete symmetry, but this argument does rely on U1.
I thought the LSM theorem applied to lattice translations plus spin rotation symmetry inside that.
Mm-hmm.
Does the spin rotation play any role in?
Well, actually, at least to show the conventional LSM, we only need U1 subgroup of spin rotation symmetry, and you can identify this U1 with the U1 subgroup of spin rotation. That is, we just need, let's say, global rotation of all the spins are about the z-axis, let's say. Yeah.
So like it's basically translation plus a U1 symmetry.
The generalization that we are deriving here seems to be sensitive to the geometry of the lattice.
Well, so to derive this, I need a periodic boundary condition. Yeah.
But it has Ly indeed, so it seems to know about the size.
Okay, so yeah, so this argument, precisely speaking, depends on this particular choice of Ly. So Ly has to be co-prime with Q, but okay, so we are expecting that once you have degeneracy for large, but some choice of sufficiently large Ly, then this degeneracy would survive for generic choice of Ly sufficiently large. And so your question is about boundary condition or?
Abstraction to that because of this geometrical.
Yeah, good question. So actually, I don't know exactly how to interpret this Ly dependence of his. Maybe Nati has better idea.
Is there a UV ionization in this case? No UV. In this case, there's not.
Good question. So like, let's say when I simulate this system numerically, I can change Ly as a discrete value. So if Ly is not co-prime with Q, you can find some degeneracy. But when the Ly is not co-prime with Q, and then like the argument is lost, but in the ground state, you probably will still find the same degeneracy. It's just that. So your argument here is just that the argument doesn't apply anymore, or there's interesting way to apply.
Well, yeah. Okay. So this argument directly applies to Ly, which is co-prime with Q, and this does not directly tells you that whether there is a degeneracy for Ly multiple of Q or something like that. But I guess on physical grounds, we expect that if there is a degeneracy, that degeneracy should come from some physical mechanism like a spontaneous symmetry breaking or topological order. And in either case, such a degeneracy would survive for generic value of Ly. But that's kind of physical hand-waving argument, not this mathematical proof. But yeah.
Do you get anything interesting if you replace the electric field by a gravitational field?
Yeah, okay, that's interesting question. Yeah. Yeah, I would be interested in that question, but yeah, honest answer is I don't know yet. Yeah.
Incorporate other lattice point groups like rotation, lattice rotation, or this for general lattices.
Yeah. So in recent years, there has been a lot of progress refining this Lieb-Schultz-Mattis type theorem in the presence of various crystal symmetries, including this discrete rotation and mirror reflection and so on and so on. Yeah, there is a bunch of papers doing that. Although I'm not quite expert on this, but yeah, I just say that there has been many recent progress on making this more powerful in the presence of various crystal symmetries.
Last question.
Do you know the number of the degenerate quantum states in systems? Does the number depend on the shape of the lattice?
Yeah, from this, because I didn't have time to make a final statement, but from this argument, if nu is P over Q, P and Q co-primes, then minimum number of ground state degeneracy must be Q, or integral multiple of Q. That is what I can say from this argument. But as I said, so sometimes if you have more larger crystal symmetry, like then you can derive larger ground state degeneracy. But from this generic condition, it's only Q-fold.
I think we'll respect our next appointment. So let's thank a speaker again and